At SimpliSafe, our award-winning home security has advanced sensors, HD cameras, and now this 24/7 LiveGuard protection. Only from SimpliSafe. Monitoring agents can see and speak to intruders through our indoor camera to help stop crime in real time and for fast police response. Now get 50% off any new system with Fast Protect monitoring at simplysafe.com/Spotify. Advanced home security, 24/7 professional monitoring for less than $1 a day. There's no safe like SimpliSafe.
This podcast brought to you by Ring. Save big right now on select Ring doorbells and cams and give the gifts that keep on giving. Find gifts that help handle all those deliveries.
Hey, again? Leave it behind the chair with the others.
And gifts that tell you when creatures are stirring.
Biscuit, get away from the ornaments. Good girl.
Shop the Black Friday sale and save up to 40% on select devices at Ring.com. That's up to 40% off right now at Ring.com.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us on yet another episode of the Space Nuts podcast. We thought you'd be fed up by now, but no, you keep asking for more, so we keep delivering. Episode 254. Good grief. I can't believe we've talked for near 254 hours about all this stuff, but people find it fascinating. I hope you do too, and thank you for joining us. My name's Andrew Dunkley, by the way, your host, and joining me again is Professor Fred Watson, Astronomer-at-Large. Hello, Fred.
Hi, Andrew. How are you doing? You're looking hale and hearty, if I may say so.
Oh, thank you, sir. You're looking wonderful yourself.
Oh, jolly good.
I've had a pretty good week, I suppose. I'm getting my first COVID vaccine injection on Monday.
Oh,
so,
good. Okay. Yeah,
that could be interesting.
Oh,
yes.
You'll enjoy it. It's a thrill. I had mine 5 weeks ago.
I'm thinking that I need to do it and then talk about it on the radio because of the negative publicity surrounding some of the effects that have been highlighted around the world. And yet you talk to the doctors and the nurses and they'll tell you, look, these things are happening in very, very small quantities and the odds of anything going pear-shaped are 1 in a million. So I'm thinking I need to do this and and I'm thinking I need to get mine and get on the radio and say, okay, I did it, and this is this is the story. But we will. That'll be next week. If I'm not here next week, you'll know that my arm's too sore to lift up and grab the microphone. That's what it.
You'll be all right.
I'm sure it'll be fine.
Yeah. I didn't have any after effects at all with mine. I had more. Yeah, more with the flu jab that I had, which gave me very, very slight flu symptoms. I know you come down really badly with the flu when you have a flu jab, but AstraZeneca did nothing.
I have in the past.
Great.
Yeah, well, I had a flu injection 2.5 weeks ago, and no side effects at all.
Oh, that's
just a bit of a sore arm for about a day, but nothing at all. But after getting the flu full on in 2018, I am religious about getting my flu vaccine now because I don't want to ever go through that again. It was horrible. Okie dokie. It's time to look at what we're going to be talking about this week. We're going to be talking about COVID-19, the AstraZeneca injection. Hang on, we've already done that. We're going to talk about heavy metals in the vapor of comets. This is a new discovery. I'm thinking Metallica was in there, banging away, and maybe a couple of other heavy metal bands of the era.
Probably Bill Haley and his comets as well from the 1950s. They'd be in there. They're not heavy metal, but they're...
yeah, for sure, yeah. And we're going to talk about where we live because I'm sorry to break this to you, but the journalist in me must report the facts. We live in a really ordinary place. I mean, in the scheme of things, it is as boring as bat poo, which is, maybe a good thing. We'll find out. We've got questions as well from Tim in Lismore who wants to know about dipping his toe into a black hole. Not a good idea, Tim. Also, the stability of our solar system. Why? is it so? Because it's ordinary. It's that's why. And Paul from Toowoomba is asking questions about magnetism and tractor beams. All that to come on this episode of Space Nuts, which we're planning to knock over in probably 3 or 4 minutes. Now, Fred, let's start with heavy metals in comet vapour. This has just been discovered, and I'm guessing there's a paper or at least some form of study that's come up with this interesting discovery, this interesting find.
Indeed, yeah. There is a paper and lots of press about it as well, because it's a really interesting result. And I should tell you that these studies use the telescopes of the European Southern Observatory down there in Chile, which are pretty well the best equipped large telescopes in the Southern Hemisphere. There are few other ones down there which are pretty damn good as well, but the 4 telescopes of the very large telescope, they're cracking good, and so they were used to make these observations. And what's interesting about this is by heavy metals, actually we should perhaps just define that for a minute, Andrew, because astronomers
good idea
have got a very funny view of what constitutes a metal. And a metal in astronomy is anything other than hydrogen and helium. So oxygen's a metal, calcium's a metal.
Oh, right.
Yeah. It's always been like that. I guess probably since the start of astronomical spectroscopy, the idea of breaking up the light from stars and finding out what signatures of elements you can get in there. But yeah, the metals are anything heavier than hydrogen or helium. So when you talk about heavy metals, you're really talking about what you and I would call metals in normal life, and in particular iron and nickel. And iron is the commonest metal in the universe. In fact, one of the commonest elements, and it's because it's a byproduct of the nuclear processes that go on inside stars when they're in their normal adult life. So iron is being created towards the end of the life of the star, actually. Anyway, the bottom line is iron is common, nickel is common. Now, there is an interesting little factoid about this, though, and that is that we find, for example, in the core of the Earth, it's an iron-nickel core, and the iron usually outweighs the nickel when you find it in nature, like metallic asteroids or the core of a planet. It's usually 10 times more iron than nickel, which is understandable because iron's more readily produced inside stars. But in this story, we find that in these comets, you've got more or less equal proportions, and that is unexpected, that there are equal proportions of iron and nickel in the comets. Now, we've known for a long time that comets must have this sort of stuff in their material. Remember, comets are icy bodies with lots of dust embedded in the ice, and that dust includes heavy metals. And the temperatures of these things are typically colder than minus 100 degrees Celsius. So they're very, very cold. And the metals normally remain very much as grains of dust, but basically not anything that's vapor. But that's the surprise with these observations. And it comes from groups in Poland and Melbourne, I think. Poland and Belgium, I think, are the main centres where the astronomers who've worked on this come from. There are 2 studies, actually. In fact, let me get it right. The first study is the solar system comets, and that's the Belgian study. The second one is our old friend Comet Borisov, which has been looked at by a group from Poland.
Boris,
that's the one, yeah. And both of them have found this unexpected result, that the metals turn up in the vapor of the comet, the stuff that's ejected from the comet when it gets near the sun, so that material vaporizes. Now, normally, these elements, they vaporize at very high temperatures, at 700 degrees Celsius or thereabouts. And we're talking here about minus 100. So what's going on? I should just clarify there that when I say vaporize, I mean they sublimate, and sublimation is the process when a solid turns directly to a gas, which happens a lot in astronomy because it's what what elements do in a vacuum, basically. Goes straight from solid to gas. It's why on the surface of Mars, which is not a vacuum but not quite, ice doesn't turn into water, it just turns straight into water vapour. So that's the process, sublimation. But the mystery, why is it that at these ultra low temperatures, these metals are turning into vapours? And I think, as I understand the research, I can quote actually from the paper, and you'll see the problem. The paper says unbound nickel atoms seem to originate from the photodissociation of a short-lived nickel-containing molecule that sublimates at low temperatures or is otherwise released with major volatile compounds. Did you get all that, Andrew? Because that's the answer.
Yes, I did.
Yeah.
Okay.
What it means is that the key word there is photodissociation. It's the radiation of the sun hitting these things, and it's a nickel-containing molecule, and basically the radiation from the sun shoots out the nickel atoms, and the same is probably true with the iron. I think that's the story, that it's all about the sun's radiation acting directly on these atoms.
If you'd asked me, Fred, to guess before you told me the answer, I would have said, I'm going to imagine it's something to do with the sun hitting the comet.
Yeah, you see,
that's what I would have said.
You should be an astronomer, Andrew, because you've been mixed up with it for too long. But yeah, absolutely right.
I'll be a journalist. We don't have to think much.
I think that's not quite true, but never mind.
Sorry.
It's. I don't think you think at all, do you? No, I never said that. Journalists, I think, have to think an awful lot, and a lot of them, these forensic journalists and investigative journalists, they're doing a fantastic job uncovering all kinds of miscreants.
It's tough work, though.
Yeah, it would be.
Don't make many friends.
No, I bet you don't. I bet you don't. It's a good job you've got me, isn't it, really?
Yes.
Anyway, going back to that, you were right on the money. It's to do with the sun's radiation. To be honest, I would have guessed something similar, but I think I would have got it wrong. I think you got it right. I would have thought, it's the subatomic particles in the solar wind that do this. And it doesn't look as though that's what it is. It's actually the radiation, the light radiation from the sun. So there you go.
Well, when I say I think it's got something to do with the sun, that's a pretty broad answer.
Yes.
That could mean anything. So that's a journalist at work.
Yeah, that's right. Make it broad. So I guess the nice twist in this is the Polish work that has looked at Comet Borisov, the first interstellar comet that we've ever observed, and found that it's got very, very similar properties to solar system comets. And in fact, some work that we talked about probably a month or so ago revealed that it seems to be like a solar system comet in every way, except it's never been near a star. So it's a pristine sample of the raw material of stars and planets. Really interesting that it's an icy remnant of the gas and dust cloud that solar system, wherever it was formed in. And this work, kind of underlines that.
Yeah, I'm not surprised the Polish looked at Borisov. It's a very Eastern Bloc name.
It's an Eastern Bloc name, that's right.
I wonder if that's why they chose to look at it. Well, just the opportunity presented itself, I imagine. And I don't suppose can we ever figure out exactly where it came from?
Borisov, no, it's kind of a bit of a mystery, really. You can see what direction it came from, but you don't know how long it's been travelling in that direction.
No.
And like our old friend Oumuamua, which came from the direction of the bright star Vega, but when Oumuamua was where Vega is, Vega wasn't there. It was somewhere else because Vega's moving as well. The comets are moving and Vega is. Anyway, so we'll probably never know where they came from, but
it's this.
Go ahead.
Same difficulty you face with time travel, because you've got to figure out where something's going to be when you get there.
Yeah, exactly.
Otherwise, you'll end up in the vacuum of space.
Yeah, the odds are that that's exactly where you'd end up, feeling very uncomfortable, probably. With that age-old question.
Not in my new book. I got it all. I got it all figured out.
Okay, good.
I actually had to rewrite a section because I'd put all the data down about the time travel anomaly, and then realised, one of our listeners actually said, how do you avoid ending up in the vacuum of space? And you were explaining the third element to time travel that would be required. And I went, I better write that in. Typed away. Got that sorted out. Yeah.
Good
but
stuff.
It is interesting that these discoveries have been made on two separate and very, very different comets, and therefore stands to reason that this is not uncommon at all.
That's right. That this actually is a lovely segue to our next story in the next segment, Andrew. That we're pretty ordinary. The solar system is probably very, very typical in many ways, although it's different in some ways.
All right. We will get on to that in a moment, but you are listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson. Let's take a short break now for a word from our sponsor, Namecheap.com. As their slogan says, search and buy domains from Namecheap at the lowest prices. This is the service the team at Bytes.com use to buy and manage our domains, and we're very happy with the service, support and value we receive. Can't recommend them highly enough. Buying the right domain name shouldn't be hard, and with Namecheap, we've found it to be anything but that. Find your dream domain and join over 2 million happy customers when you register with Namecheap. Trusted with over 10 million domains, you'll find you're in safe hands when it comes to turning your website idea into reality. They also have excellent tools to find the right name for you, like their handy search engine. Just type in your desired name, cross your fingers, and press search. If what you were after is already taken, they'll offer up some great alternatives. And if you're looking for some inspiration, try the new website domain name finder Beast Mode and discover thousands of domain names fast. We've found their prices to be excellent, management tools intuitive and easy to use, with excellent customer support should you need it. All in all, a great experience all round if you're looking to pick up a domain name or 2 or 3 or whatever it is you need. To check them out and help support us at the same time, just visit spacenutspodcast.com/namecheap. That's spacenutspodcast.com/namecheap. And Namecheap is one word. You'll be glad you did, and you'll find the URL details in our show notes and our website. Just visit the support page. Now, back to the show.
Space Nuts.
Now, Fred, our patron numbers are increasing, which is fantastic, because we have been appealing for people who wish to voluntarily become patrons of the Space Nuts podcast. You can log on to our website, spacenutspodcast.com, click on the supporter link and find out how you can be a supporter of Space Nuts, whether that's through a regular monthly payment through Patreon or Supercast, or a one-off donation, or maybe just spending a couple of dollars through the Space Nuts shop. Totally up to you, totally voluntary. You don't have to do any of that. You can just tune in and listen every week if you so desire. But the goal is for us to get patron numbers up to the point where it's self-sustaining and we rely less on third parties. Although we thank them for their support too. I mean, people are coming to us pretty regularly now wanting to support the Space Nuts podcast, and we so appreciate that. We've got some wonderful collaborations in development at the moment, and we've got some new ideas we're working on. Just a few things that we think will value add to the Space Nuts podcast. These are what's the term to use? In development. So we will tell you more about those as they get closer. But thank you to all our patrons, all the people who put their money into the podcast to keep us alive and kicking, and to make sure the batteries don't run out on Fred's machine that he has to turn on every night when he goes to bed. Also thank you to our Space Nuts YouTube followers, who are numbering 1.72 thousand now.
That's pretty impressive.
Makes it sound like a lot. But we've got 1,720 odd, and they're all odd because they're Space Nuts listeners or viewers on YouTube. Why you put up with our faces, I do not know, but we thank you for that. All right, Fred, let's go from the extraordinary to the ordinary, and that is where we live in the universe. It's apparently not that flash. when it comes, down to it. It's the ghetto of the universe.
It's
maybe it's not that bad.
I mean, you're using the word ordinary in its Australian context, which means bloody awful, doesn't it? Well,
that's right.
That's pretty ordinary, mate.
I should clear that up. Yes, in Australian, when we refer to something as ordinary, it means it's absolute garbage.
Terrible. But ordinary, perhaps regular or common or something like that is a better word for what I'm going to talk about, which comes from work done by colleagues here at the University of Sydney, here in Australia. And once again, they've used the fantastic facilities of the European Southern Observatory. It's a big plug for ESO today. This is a really nice story, and actually it's got links with work that I've been involved with the RAVE survey and the Galar survey of stars in our galaxy, which we've talked about before, so I won't talk about again. But it's a topic investigating a topic called galactic archaeology, which is how galaxies are put together and what you can learn by looking at the constituents. So, two of my colleagues in the RAVE survey many years ago discovered that our galaxy has not just one but two disks. Now, when we think of galaxies, we usually imagine these lovely spiral structures, and our galaxy would look like that if we could see it from the outside, that being one component, and another being a much more rarefied halo spherically distributed around it of old stars and globular clusters, and they're the main constituents of galaxies, plus the nucleus in the middle, the central core. But these colleagues of mine, back in probably the 90s, I think this was, they discovered that the disk is not just a single disk. It's got two components, which they named the thin disk and the thick disk. Really good names, because that's kind of what they're like. So the thin disk, and that's what you see when you're looking at the Milky Way, you're seeing the disk of our galaxy. It's about 1,000 light years thick. And it's the sort of central part. The thin disk sort of envelops that. It's about the same diameter, but thicker, several thousand light years thick, and much less dense. It's there are far fewer stars in the thick disk. And this was the key thing. And this is really what distinguishes them. And it goes back to what we were just talking about metals, heavy metals, because the thin disk, where the sun is located, which is the Milky Way that we see, that's rich in these heavy metals, that the heavier constituents, the iron, the nickel, all of these things that tell us that we're looking at a population of stars which are relatively young, and that's because they've been formed from a very rich soup of gas, the interstellar gas, which has been enriched by previous generations of stars, if I can put it that way. So our Milky Way stars they're kind of like the sun. They've got the composition of the sun, whereas the thick disk stars are much more ancient, and that comes about because you can tell that they've got far fewer of these metals in their spectrum. So the spectrum's much more like primitive stars that existed hundreds of millions, tens of billions. I keep mixing up my millions and my billions, Andrew. It's
That's okay.
Several billion years ago. Let me put it that way.
Right.
So that's a time in the past when the stars that were shining then had fewer of these heavy metals in their spectrum because they hadn't been generated yet. They hadn't been made by those generations of stars. So the thin disk and the thick disk are separate. They're distinct in the sense that the thick disk is an older structure. So when scientists tried to build models of how you might form a thin disk and a thick disk with these properties, they ran into trouble. And the only way that you could get this structure was if you had quite specific events where you have a medium-sized galaxy in collision with ours, something like 9 billion years ago. And that is a process that's pretty rare. We know that galaxies eat up other smaller galaxies, but big galaxies colliding is a bit rarer. And so the suggestion was that our galaxy was unusual because it had had this rare collision 9 billion or so years ago. So, that was one of the reasons why we thought our galaxy wasn't pretty ordinary, that it was maybe quite unusual and maybe richer in these metals than other galaxies. And of course, that plays into things like the origin of life and all of those issues, how much carbon you've got and things like that. So what these scientists have done is looked at other galaxies that are similar in appearance to the Milky Way, our own galaxy, using an instrument on the Very Large Telescope down there in Chile, and measured the spectra. And they found at least one, which rejoices in the name UGC 10738. It's about a third of a billion light years away, so 320 million light years. And the nice thing about that galaxy is we're seeing it edge on. So you're seeing it, from the side. And that means that you can actually look at the thin and thick disk stars separately. And that's what they did. And guess what? They found it's just like ours. I'm quoting because there's a conversation article on this, which is well worth looking at. It's called "Stellar Secrets of a Distant Galaxy Suggest Our Milky Way Isn't So Special After All." And what the authors say is we found, and they're talking about UGC 10738, we found metal-rich, magnesium-poor stars concentrated in a thin disk along the galaxy's centre, with a distinct group of metal-poor, magnesium-rich stars above and below this in the thick disk region. This distant galaxy is remarkably similar to our own, which in turn means there's probably nothing that's remarkable about the Milky Way after all. I just discovered a typo in the... Oh, no, it's not a typo. There's nothing that remarkable about the Milky Way after all. I should read it properly. Sorry, chaps, if you're listening. The issue I didn't mention of the magnesium-rich and magnesium-poor, that the thin disk stars are magnesium-poor. The thick disk stars unusually are magnesium-rich, and this comes about because of the way these materials, these elements, are formed over generations of stars. It's the central pillar of the study of galactic archaeology, is looking at these different elements and seeing how they're spread throughout the spectrum of the how much there is of them in the spectrum. So the conclusion is we're maybe not that unusual.
Yes. So rather than being boring and uninteresting, it's just we might be more common than not.
That's right. If I could just go on and read a bit more of the conversation article, which is, by the authors I've mentioned from Sydney University. Our discovery has several implications. First, it suggests the disk features in the Milky Way might be the result of a standard formation path that all galaxies follow. And this is backed up by the identification of similar structures in non-Milky Way-like galaxies. And second, the fact that our galaxy is relatively normal is extremely exciting. It implies the Milky Way can act as a blueprint or template for galaxy formation. Means our home galaxy could hold the key to unlocking the cosmic history of the entire universe. And finally, and being a little speculative here, the Milky Way is the only galaxy that we know contains life. New research has suggested... I was
going to mention that.
Yeah, there you go. Basically, it's saying that, we're a home for life. Maybe other galaxies are too.
Well, it stands to reason, doesn't it? And certainly something you can't dismiss. I know people who absolutely and utterly believe in advanced civilizations beyond Earth, and maybe so. Whether or not we'll ever be able to communicate or contact them or find them remains to be seen. Some analysis of exoplanets may reveal the potential for civilized beings, but at this point, we have evidence of one planet in the entire universe that harbours life. And that's, I don't know where it is. But anyway, it exists. Now, the other question I have is with the ordinariness of our galaxy, will that change in a few billion years when we merge with Andromeda? Because they'll have to rewrite this paper.
They will, 4.5 billion years down the track. Yeah, because our galaxy, what will happen is, first of all, probably most of the stars will miss each other, so there won't be direct collisions. But both Andromeda and the Milky Way are pretty rich in hydrogen, which is the raw material of stars. And when this interaction happens, there'll be a lot of gravitational disturbance, which will cause a lot of stars to form. There'll be a rapid burst of star formation, sort of using up the hydrogen. A lot of young stars which pop off at the end of their short lives as supernovae. And then the end product will be probably an elliptical galaxy. And elliptical galaxies, as their name implies, they look the shape of rugby footballs. And they have very little gas because it's all gone. It's all been used up by the stars in them.
I don't know. Those footballers have a fair bit of gas.
That's a different sort of gas. Yeah. But that's right. It will change the character of our galaxy altogether. A lot of astronomers are already giving that end product a name, which is Milkomeda, because it's the Milky Way and Andromeda. Oh. So Milkomeda is the elliptical galaxy that'll be the end of it, and somebody else will write a paper on that in some other universe, I'm sure.
They got that reading trashy magazines about Bradulina, I reckon.
Probably, whatever that is.
I'll explain it one day.
Yeah, you'll have to explain it.
You really don't need to know, though, Fred, honestly.
Okay.
Ask Marnie.
I'll ask Marnie, yeah.
Oh, dear. I could get in trouble now. But, yes, it is interesting, and the fact that we are probably not ordinary is not ordinary, and that's a good thing by the sound of it.
Two different ordinaries there, that's right.
Could open up the way to further analysis and maybe answering some of the questions of the universe.
Yeah. Sounds good.
This is the Space Nuts podcast. I used to know a shop owner named Mr. Nuss, but that's got nothing to do with us. Here on the Space Nuts podcast, Andrew Dunkley and Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, I did mention patrons earlier on, and I also mentioned our website, which I'm going to mention again, because why do something once when you can do it multiple times? But our website, if you haven't visited, spacenutspodcast.com, is the place to go to catch up on Astronomy Daily, all the latest stories in the astronomical world. We have a feed there. We have the shop, which offers, memorabilia. We've got stickers, we've got mugs, we've got caps, we've got shirts, we've got all sorts of stuff. By the way, I don't know if I can reach because I've got my headphone in, but I have got... I'll be right back.
Ladies and gentlemen, he's gone.
I've got to put my headphone back in. But I have got hard copies of my book. They got delivered the other day.
That's very good.
And I got an instant request from one of our listeners when I posted the video of me opening the box, which I did blind. I hadn't looked at them, so if they were all weird, I was going to embarrass myself. But to Marie Claire, there's your book, autographed as requested.
Very good.
So that's going to be on its way to you, and thank you for putting your heart behind the podcast. We appreciate your support. She's been a great supporter of the podcast through her Instagram and Facebook pages, and she wanted the first one. So there it is, ready to go. That will be in the mail in 1 or 2 years. Just letting you know. No, I'm just waiting a bit because she's moving to her place in Florida, so she doesn't want it to arrive before she gets there. Otherwise, it could end up anywhere. But I will make sure that gets to you in a timely manner. But yeah, our books are on the Space Nuts shop, and you can also click on all the other links and find out all you need to know about astronomy and what makes us tick, because we don't know. maybe that's something that should be studied. Now, Fred, let's get into some questions. The first one comes from young Tim. I don't know how old Tim is, but he's in Lismore in northern New South Wales.
Hi, Fred and Andrew. It's Tim here from Lismore, far north coast of New South Wales, God's own country. Love the show. Been listening since about episode 50. Mind you, wife and kids think I need to get a life. A few questions, but I'll limit myself to two. So there's been a lot of talk recently about black holes and spaghettification. My question is, how thick is the event horizon? So I know you've mentioned that recently there's been a event horizon that's like 3 times the size of the solar system, but how thick is that event horizon line? So with Hawking radiation, it seems to indicate that it's razor thin. But to me, that just doesn't sound right. So if I dip my big toe across that event horizon line, is it going to be spaghettified, but the rest of me is going to be okay? So that's question one. Question two is, how are the orbits of the planets so stable? Surely planets and suns are expanding and moving, are all zipping around the universe. How we seem to be relatively stable, or is it just that my timeline's so small? I would have imagined everything's whizzing and crashing and bumping into one another, but everything seems to be moving along okay. Thanks very much. Keep up the good work. Bye.
Thank you, Tim. The whizzing and crashing and bumping into each other, that's just standard traffic on the Pacific Highway around Lismore, I imagine. And I can answer his second question, the stability of the solar system. It's because we're ordinary. We're
ordinary, that's right.
But no, in all seriousness, we'll start off with his first question. If he dipped his toe into the event horizon of a black hole, would it get spaghettified and the rest of him would be okay? I suspect not.
I think you're on the money there, Andrew. It's a great question. Look, I've never been asked before how thick is the event horizon. I love it. It's great.
Yes.
But it doesn't actually have a thickness. So the event horizon, in a sense, is an illusion. It's just that it corresponds to, it's a sphere. But every point on that sphere is a certain distance from the black hole, and that's the radius of the event horizon. But what the event horizon is just that point in the vicinity, or that distance from the black hole in its vicinity, where light can't escape. So it's not really to do with the spaghettification. The point being that if you approach a black hole, long before you got near the event horizon, you'd be feeling this extreme gravitational field, and you'd be spaghettified already. It's just that at the event horizon, all these peculiar phenomena involving photons, which are particles of light, that's where they start happening, most notably the fact that light can't escape from the event horizon. And a particle of light on the event horizon is just whizzing round and round. It's in orbit. That's the key thing. So, dipping your foot in the event horizon, it's a lovely idea. I'm sure that's good material for your next book, Andrew. But it doesn't work like that. The event horizon is just this particular distance where light can't make it out. And so, but you're already spaghettified. So in a sense, it doesn't have a thickness. Basically it's a boundary between one situation and another. And I suppose an analogy to that would be the surface of the sun, which is where the light seems to come from, and you can't see any further down. But there's no, there's no big transition. It's just the pressure increasing as you get nearer the centre of the sun. That wasn't a very good analogy, but it's the best I can think of.
No, fair enough. But I foresee a time, because I see where Tim's coming from. I foresee a time when interstellar travel's a thing, that they're going to have to put wrong way, go back signs up around all the black holes.
Yeah.
Because people will just want to go and have a look.
Yeah.
And you know how inquisitive we are. We'll get too close and...
That's right. It'll be like...
but the Italian restaurants will do well.
I'm not sure I perceive the link there, Andrew. I was thinking more
Spaghettification?
Oh, spaghetti. Okay, there you go. God, I'm so slow today. It's been about a week.
Because we're ordinary, Fred. That's what it is.
I was thinking, though, my thoughts went to Hawaii, where exactly what you've described happens. People go to look at the lava flows and just get too near, and all kinds of horrible things happen to them.
Yep.
And that would be the same with a black hole.
I've actually done it.
Yeah, I'm sure you have. You melted your shoes and things like that. Italian restaurants need to be well enough away, but isn't it a great, spaghettification restaurant would be a great selling point for the 300 people in the world who know what spaghettification is.
Because there is a restaurant at the end of the universe.
There is, that's right.
Now, moving on from that, the stability of the solar system. Why is it so? Why isn't stuff crashing into each other? Well, I guess it still is, just not as dramatically and as regularly as it used to at the beginning.
That's right. Exactly so. So in its early history, 4.57 billion years ago, the stuff was charging around all over the place, and it was exactly as Tim describes. Everything was crashing and bumping into each other, and that's what forms planets. But the planets, as they build, they get more and more massive, and that sort of gives them a bit of a clout in terms of how their gravitational influence is enough that they can adopt stable orbits. Although it has to be said that we think that in the history of the solar system, particularly the giant planets, their orbits have probably migrated in and out a bit. And in fact, there's a possibility that at one time Neptune and Uranus were in a different order, that Uranus was actually the furthest planet. But that's a much more, it's a much slower process. We're talking about things over hundreds of millions of years. So it's kind of crashing and bumping into each other in slow motion, if I can put it that way. Everything settles down. The things stabilize. Another example is the Trojan asteroids. These are these two groups of asteroids, and there's 9,000 of them all together, which are in Jupiter's orbit, but clustered 60 degrees ahead of Jupiter and 60 degrees behind Jupiter. And what that's saying is, asteroids you'd think of would normally be in Jupiter's orbit, would normally be colliding with Jupiter, but Jupiter's got such a huge gravitational influence that it forms these stable positions, the two Lagrange points, in front of and behind it, where asteroids cluster. So it's a kind of gravitational tidying up of the solar system, and that's basically what's happened with all the planets, resulting in a very stable situation, which is just as well if you're trying to evolve life on a planet, and in particular intelligent life.
Yes, I would imagine if things were unstable, we would never have came into being.
We wouldn't have made it. No, that's right.
Possibly. No. All right. Thank you, Tim, for your questions. Very good. Let's move on to our next set of questions from Paul, also in Australia. He's up in sunny Queensland.
G'day, Professor Fred and Andrew. This is Paul from Toowoomba in Queensland, Australia. I've got a question about magnetism and tractor beams. I understand that some scientists down at the ANU in Canberra have managed to create a tractor beam using a laser. Is this because light is magnetic in nature, as you mentioned back in, I think it was episode 246, Professor Fred? If so, cool, but can you explain how it works in terms that my Year 5 and Year 6 students at Darling Heights State School could understand? That's actually just an excuse. I won't understand anything more advanced than that myself. Anyway, can't wait for both your books to come out. Or at least one of them is going to be going on the shelf of my mini library at school. And congratulations also on over 1 million downloads and more than 250 episodes. It may have come as a surprise for you, but it sure as heck wasn't any surprise for us fans. Long may your work continue. Thank you to you, Professor Fred, you, Andrew, and you too, Hugh. Amazing work. Can't wait to hear more.
Thank you, Paul. Thank you for the good wishes. Lovely to hear from you. I'm guessing I know which book's going to end up on the library shelf at the school. And sorry about that, Fred, but anyway.
Yeah, that's a shame, isn't it?
Okay, tractor beams and magnetism.
Paul, thank you very much for that. And just in case you didn't want to put his book on the shelf, I think it looks as though my new book's going to be called. Actually, I can't remember what it's going to be called. Space Warp. It's had so many names. I think it's Space Warp. Yeah. All right.
So what was it?
Space Warp. Yeah.
Like it.
Yeah, I do too.
Yeah.
It's actually the name of one of the chapters as well. Great to know that people, find our stuff useful, particularly with the year 5 and 6 students, because they're the people who are the future. They're the ones who are going to put interstellar spacecraft in space and things of that sort. So great to have teachers listening. Okay, so how does Paul is right? There have been tests done. It's actually not the ANU. It's a company which is right next to the Mount Stromlo Observatory. They've got strong links with Mount Stromlo Observatory, which is the ANU, but they're a kind of spin-off. They are called Electro-Optical Systems, or EOS, and their speciality is dealing with trying to ease the problem or relieve the problem of space junk. There is, I think I'm right in saying, because I was involved with the beginning of this, there is what's called a CRC, a Cooperative Research Centre, which is called, it's the Space something Research Centre, I can't remember what it is, Space Debris or something like that, which EOS is part of. There you are, there's half a dozen acronyms in there. So you can see it's a complicated process. But yes, they have indeed done this business of using lasers to push small pieces of debris out of the way in space. And they do some very, very clever stuff. But the basic principle, which is what Paul's asking about, is it's not the magnetism so much. Yes, you're right. Excuse me, light is an electromagnetic wave. It's a vibration of the electrical and magnetic fields in space. So magnetism is involved, but it's in some ways a more, excuse me, a magnetic frog in my throat there. It's a more physical process, if I can put, than that, although magnetism's pretty physical. It's to do with the momentum of photons. And light particles, which are photons, have a momentum, even though they are massless when they're stationary. We're getting to some intriguing physics here, but if Paul's teaching physics at all, you know that the momentum of something is the mass times its velocity, and that really relates to the amount of energy that this moving object contains. So I have fairly zero momentum at the moment because I'm sitting still, but if I was running along, my mass and my velocity will be the product. But light's intriguing. Light particles have momentum, but they don't have any mass, because they don't have what's called a rest mass, which is the thing when it's stationary. Mass changes with velocity because of Einstein's special relativity theory, and at the speed of light, particles effectively do have mass because they have momentum, and it's the momentum that's being transferred from the photons to the particles that allow the beams to be, the bits of space junk to be moved. There's another very well-known, example of this, Paul, and that is the idea of light sails in space. And these have now been tested. There's at least one experiment been done to show that you can use a light sail to collect the momentum of the sun's light and change the orbit of a spacecraft. It was an experiment that was conducted last year. So light sails do the same thing. They take photons of light, which are coming from the sun, and they're pretty energetic. And then some of their momentum is transferred to the solid surface. The light sail gives it an acceleration if you've got enough of them. And that's the same principle as actually using a laser as a tractor beam to move things around in orbit. That's a fairly long-winded and complex explanation, but that's kind of what's happening. So it's worth checking up on. Just check up on the momentum of light and how it moves solid objects.
Yeah, I mean, I understand the concept.
You're still there? Yes, you're still there.
Yeah, I'm still here.
I lost you for a minute, Andrew. I thought you'd gone to sleep.
No, never do that to me, Brett.
I think we've got a poor connection.
I understand the concept I understand the concept of sails catching a breeze, but is it exactly the same concept in space with light sails catching light or photons, or the momentum?
Yeah, I think it is, because it's the atoms of air. When you're talking about a sail catching a breeze, that's the atoms of air are transferring their momentum to the sail and giving it a push, an acceleration. So I think it's basically the same principle. And I guess the real bottom line in this is, as with a sail in a sailing boat, how do you control it? You need to get all the angles right and things of that sort. And that was the neat part about that experiment that was done with the light sail last year. I think it was a spacecraft called Light Sail 2, which was funded by the Planetary Society, if I remember rightly. And what they showed was that you can actually use your light sail to give you an acceleration that is controllable. In other words, you tilt the light sail at the right angle. Because what they did was they changed the orbit of the spacecraft very, very slightly, but enough to show that it was working.
Feasible. No, it's fascinating. What would light sails need to be made of?
They're usually made of mylar.
Wouldn't be canvas.
Mylar sheet. Yeah. Well, mylar's it's a thin, really thin polymer. It's basically what you use in, it's the silver paper that you use in the oven and things like that. It's that kind of thing. A very thin film. In fact, no, it's not the silver paper. It's the stuff you use to wrap up your, something like Glad Wrap, which we have here in Australia, which is a food wrapping thing. I think that's mylar. I think that's a mylar sheet. And what you do is you aluminize it. You coat it with aluminium to make it reflective.
All right. So I could make a light sail in the kitchen, just get some cling film and put a piece of aluminium foil behind it. And voila, I've got a light sail. You have.
You have a light sail. Your problem would be that you'd have to pump all the air out of the kitchen to make it work. And that might not be quite so good.
Yes, I knew there was going to be a trap. Yeah. There's always something. Yes. All right. There you go, Paul. Hopefully that's answered your questions this week, and thank you for sending them in to us. And if you would like to send us some questions, you can do that by clicking on the AMA tab on our website. You can send us your message through our email system, so you can text it to us, or you can record it if you've got a device with a microphone. We love to hear your voices, but either way, we will get them and we will be able to add them to the mix. So thank you again to Tim and Paul. And thank you, Fred. That brings us to the end of yet another episode.
It does, doesn't it? Amazing how they all happen.
Yeah.
It's a great pleasure, Andrew. Thank you very much for putting up with me too, and I look forward to episode 250. Sorry, 260. No, 255.
Yes. 55's next.
255.
55's next. It's all good. It's all good. Go and have a nap. Yes, thank you, Fred, as always. We'll catch you again next week. Professor Fred Watson, Astronomer-at-Large, part of the team here at the Space Nuts podcast. And hello to Hugh back in the studio, who has now got some heavy editing to do with heavy metal, for sure. And from me, Andrew Dunkley, thanks for your company. See you again on the next episode. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.